Hello physics students, this is Dr. Brenzy here. This is a video on lesson 4.1.1, and our objective for this lesson is that we will be able to define and calculate the following properties of an object, one being momentum and another being what's called impulse. I'm sure you may remember momentum from your basic physics class way back in 9th grade. Maybe you don't, but we're going to review what that is, and then we're going to go on to this term that's less likely you may have heard of, and that is called impulse. Before I talk about momentum, though, what I want to ask you to kind of wrap your head around this concept is, answer this question: would you rather get hit by a soccer ball traveling 60 miles per hour, or would you rather get hit by a bowling ball traveling 10 miles per hour? Well, in class we had this debate, I guess. We had a lot of people chose a soccer ball, but there were a few people who actually chose getting hit by a bowling ball traveling 10 miles per hour. But the point I want to make with asking this question is that sometimes it's important not only to consider how fast an object is going, but also its mass. You may recognize, or you may answer this question based on the fact that a soccer ball has less mass than a bowling ball. So you would say you'd rather get hit by a soccer ball traveling 60 miles per hour. So sometimes it matters how much mass an object has. Well, that's where the concept of momentum comes in. Momentum is the product of an object's mass and velocity. So we would say that it's momentum P. P stands for momentum, and momentum is a vector. It cares about both direction and size, or it has both direction and size. And that momentum is equal to mass times velocity. And velocity also is a vector. One thing you may notice is, or actually maybe not notice, but one thing I want to point out to you is that the direction of your momentum vector and the direction of your velocity vector are the same. So if you know which direction your velocity vector is, then you will know what direction your momentum vector is pointing in. The units that we use for momentum are what are called kilogram meters per second. Or you can say kilograms times meters per second. Unfortunately, we don't have a special name for this unit like we do for force, which is newtons, or joules for energy, or watts for power. I guess momentum just didn't get that sort of special treatment like those other quantities did. But hey, it is what it is. So we got to get used to calling units of momentum kilogram meters per second. Now, unlike velocity, momentum takes into account an object's inertia. If you remember back from Unit 1, inertia is an object's resistance to change in its motion. And if you think way back then, you will remember that an object's inertia depends on its mass. The higher the mass something is, the harder it is to change that object's direction of motion or velocity. So we would say that a massive object, or an object with a lot of mass, has also a lot of inertia. So the quantity of momentum takes this into account because we are multiplying mass times velocity. So let's go through a couple of examples here. Actually, just one example, but it's split into two parts. So let's say that we do have a 0.5 kilogram soccer ball traveling to the right at a velocity of 27 meters per second. what is its momentum? And if you're curious why I picked 27 meters per second, well, if you convert that to miles per hour, you get 60 miles per hour. So we're actually going to calculate the momentum of a soccer ball traveling at a velocity of 60 miles per hour. Well, we know that momentum equals mass times velocity. That's our formula. So I just need to know the mass of the object, and that is 0.5 kilograms. I need to know the velocity, which is 27. Now remember, velocity is a vector, so direction matters, which is why I put this, positive sign in front, because I want to remember that this has a direction to the right. So if I multiply these two quantities together, 0.5 times 27, I get 13.5, and the units of measurement are kilogram meters per second. Now, the momentum vector has the same direction as the velocity vector, so if our velocity vector is pointing to the right, our momentum vector is also pointing to the right. And that's why we have a positive sign here. So these two, when you're dealing with just one dimension, the velocity vector and the momentum vector should have the same sign. Okay, so we've calculated the momentum of a soccer ball traveling at 27 meters per second. Now let's say that the ball bounces off a player's head and travels now at a velocity of 18 meters per second to the left. Calculate its change in momentum. Well, in order to calculate its change in momentum, we have to figure out what momentum it ended up with. We know what momentum it started with, but we have to figure out what it ended with. So let's write down our formula for momentum again. And now let's plug in mass and velocity. Oops, I got a little ahead of myself there. This is velocity, but now you'll notice that I put negative 18 here because now the velocity is 18 meters per second to the left. So that's why there's this negative sign down here. I multiply these two together and I get negative 9 kilogram meters per second. Well, that's not my final answer because I need to figure out what the change in momentum is. So if we want to show somebody what the change in momentum is, we would write down delta P, delta meaning change, equals its final momentum minus its initial momentum. Well, the final momentum is negative 9. The initial momentum is positive 13.5. So I would write negative 9 minus, because there's a minus sign right here, and then in parentheses put positive 13.5. Now when I take the difference of those, negative 9 minus 13.5, I get negative 22.5 kilogram meters per second. And I have a negative sign here because this momentum vector is pointing to the left. So its change in momentum is equal to negative 22.5 kilogram meters per second. All right, I'm going to modify this a little bit. Now I want to talk to you about a concept called impulse. Now, impulse is simply a force applied over time. So if I am pushing on something with a force of 10 newtons and I do that for 3 seconds, then I could calculate the impulse that I exerted on that fridge. We usually designate impulse as a capital J, and that is equal to the product of force times a change in time. Now this formula works if the force is constant over this delta t. If it doesn't, then we have to change this formula slightly. We have to say that impulse equals the average force times delta t. So if force is not constant, then we have to use average force instead of using our constant force. Now there's a thing called an impulse momentum theorem, which states this. An impulse, a force exerted over time, causes an object to change its momentum. So we can say that impulse equals change in momentum. Now, if the mass of our object doesn't change, in other words, if we don't lose mass or gain mass, and you might be wondering, when in the world would that ever happen, Dr. Brenzy? Well, sometimes in collisions, things can fly off, things can break, and those are situations where mass will change. But for a lot of situations, we can say that the mass of this object doesn't change. No mass is lost, no mass is gained. And if that is true, then what we can write is we can say that the change in momentum is equal to mass times its change in velocity, which means we can calculate impulse if we know the mass and if we know how its velocity changed. Now, I do realize that I'm giving you a lot of formulas here, but we're going to keep practicing this, and over time we're going to get a lot better at applying these different formulas. But probably the most important ones are definitely these two, and you'll definitely want to remember that you can use this. And then I would say this is also pretty important right here to know. Well, I guess that probably wasn't as helpful as I thought it was going to be because I pointed to almost every formula there. All right. Now, this I want to address to just the AP students. And what I'm actually going to do is I'm actually going to prove to you. Let me back up here. I actually want to prove to you that this statement has to be true. In other words, that impulse does actually equal change in momentum. So I'm going to prove that for the AP students. And if you're an advanced physics student, you can either stick around or you can decide to zip ahead in the video to my next slide. So we know that impulse is equal to force times change in time. And in this case, I'm going to assume that the force is constant. So I can write force equals mass times acceleration. Well, let's replace acceleration with the change in velocity over the change in time. Well, I can replace this F with this expression right here. So now I have J, impulse, equals momentum, or not momentum, mass, times change of velocity over change in time. And then don't forget, I'm multiplying force times delta t, so I actually am multiplying this entire thing also by delta t. Well, we see that we have delta t, those divide out. So now our impulse is simply equal to mass times change of velocity. Well, change of velocity is our final velocity minus our initial velocity. If I use the distributive property to distribute mass, then I have mass times final velocity minus mass times initial velocity. Well, mass times velocity is momentum, so my impulse is equal to my final momentum minus my initial momentum. Well, that equals the change in the momentum of our object. So, by starting off with a definition of impulse and using Newton's second law, we can actually prove that it has to be true that the impulse equals the change in momentum of the object. Or you can say that an impulse exerted on an object changes that object's momentum. So let me go through one example and wrap up with this. So we have an example here where we have a cart kind of like one of those Pascal carts that we've used in a couple of our labs. Initially, it is moving 1 meter per second to the left, and then afterward, whoa, I'm getting a little ahead of myself here. Afterward, what it does is it bounces off of this wall and actually springs back, and then so afterward it's actually moving toward the right at 1 meter per second. So you can think of this as a before and an after picture. So part A asks, what is the impulse on the cart? So, well, I can use the impulse momentum theory to state that the impulse is equal to the change in the object's momentum, which is equal to mass times change of velocity, since we haven't gained or lost mass. So the mass of our cart is 10 kilograms. The change in velocity is our final velocity, 1 meter per second, minus negative 1 meters per second, because that's my initial velocity. Well, 1 minus negative 1 is 2, so 10 times 2 is 20. And my units of measurement for impulse are kilogram meters per second. Oh, and here's some Christmas music again. All right, sorry about that. Now for part B, what is the average force required to change the momentum this much? Well, you need to assume that the force is applied for 0.2 seconds. So in other words, what force does this wall exert on the cart while the cart is actually in contact with the wall? Well, we can calculate that. We know that impulse is equal to, well, actually I might have this here already, hold on. Impulse is equal to average force times delta t. If we divide both sides of that equation by delta t, then I can calculate the average force by taking the impulse and dividing it by delta t. We know what the impulse on the cart is. That's 20. We divide it by the change in time, or the amount of time that the force is applied, which is 0.2 seconds. And when I divide those two, I get 100 newtons. So the average force that is required to change the cart's momentum this much is 100 newtons, and we need to apply an average force of 100 newtons over 0.2 seconds. Okay, so that's all I have to show you for lesson 4.1.1. And look forward to seeing you in class very soon. All right, have a good night. Bye.